Okay, so today we are talking about Fourier Transform, and again, it's a little bit difficult to say why that specific transform is so useful, but what is useful is discretization of that kind of transform and doing the same thing in computer when you sampling your signal essentially. This thing is extremely useful. Fourier transform itself is more theoretical tool to understand why whatever you'll be doing in the computer works. So it's more theoretical thing, and the only thing that you need basically to understand from Fourier is those two formulas. You have x of omega, which is defined as an integral from minus infinity to plus infinity, signal in time, and then exponent minus j omega t dt. This is formula number one. Formula number two is how you go back, which is inverse transform. So again, integral on x of omega t j omega t dt. Very similar. Inverse Fourier transform is very similar to the Fourier transform itself. Also, it's very similar to whatever you're computing as ck coefficient in Fourier series. Right? So if you take in that formula and replace it with ck, replacing omega with 2 pi over t multiplied by k, you then basically get ck coefficient. Very similar. They are coming from the same kind of idea and the same source. Now, basically, if you are talking about lecture on Fourier transforms, that's it. This is a lecture. This is all you're supposed to get from that lecture. Other than that, it's just computing those integrals. Now, this is not that simple. So here I will go in that class, I will go through different tricks which are associated with those two formulas. So not always you need to really to compute those two formulas and to get that as a result of those formulas. Sometimes you need to think a little bit more and to get other way of solving questions, especially in tests, because solving that kind of complex integrals might be difficult for even simple functions. But sometimes you're using that as is. Okay, so those are two formulas. Essentially, this is representation of any function that you want, which doesn't have to be a periodic function even. As a function of spectrum, so this is spectrum. Absolute value of that is amplitude spectrum. Phase of that function is phase spectrum. And square of absolute value is power spectrum. Okay, so this is also you need to remember. Sometimes you have to plot those things. Now, omega, essentially we call it frequency, but it's angular velocity, essentially. It's not exactly frequency. It's 2 pi f. So it's 2 pi times frequency. But sometimes we just call it frequency for simplicity. So this is all about notation. Now, questions that you might find a little bit difficult are questions related to physical properties of different things, where we are trying to relate textual information to actual question. And this is where troubles happen. This is where you might misunderstand the question itself and then to solve it incorrectly because you don't understand the question, actually. So understanding question is important part. And let's take some simple examples of that. This will be electric engineering question. Capacitor discharged through resistor. Okay, so you have capacitor, you discharging the capacitor through connecting the resistor in parallel to the terminals of the capacitor, and the current which flows is modeled by exponent times step function. And alpha coefficient here is positive. Now you need to find Fourier transform of that signal, whatever. Now, first of all, you need to understand what you are asked to do. If you are asked to find Fourier transform of the signal, you can discard all of the fluff around, which means you just ignore all of that long story, get to x, put it here, and compute whatever. That's it. This is the entire question. Now, how can you do that? What are the two ways to do that?
Look at the table.
So, way number one, looking at the table and finding the transform, and then you will have the answer if you have that in the table. If you don't have that in the table, then what?
Calling for the table.
I mean, you could manipulate it to be so it looks
So
like
you can manipulate it to be close enough to the table, and then using all kind of rules, combining different multiple things to make it like in the table, which is using scaling, translation, maybe you need to do also superposition of some kind, or gain, multiplied by all kind of constants, or to use some other rules that you have in the table. And sometimes you need to use actual definition. In that case, it's kind of easy to use this definition if you want. You don't have to, but you can, unless otherwise stated in the test. Okay. So you just take in that in the table, and you find some transform. You can also compute it directly just by putting that thing in that formula. Now, another question that could be asked on that kind of question is plotting the amplitude spectrum and plotting phase spectrum of that signal. How should we do that?
you still have to get the transform right, and then
First of all, you need to have the transform. So let's say this is what your table tells. So the x omega on the table will be 1 over alpha plus j omega. Now,
the magnitude is the
so what is magnitude of that thing?
1.
No.
1 over alpha,
So that's absolute value of that thing.
omega 1 over alpha.
So it's absolute value of 1 alpha plus j omega, right? So it's 1 over absolute value of alpha plus j omega. Right, because absolute value of 1 is 1. Now what? What is that? What is absolute value of alpha plus j omega?
Alpha squared plus omega squared and theta squared.
Alpha squared plus omega squared. That's it.
Theta squared.
And square root of that. Why is that? A complex number. This one is real, this is imaginary. This is alpha, this is omega. Right?
Yeah.
Mm-hmm.
So what is the size of the vector? Pythagoras here.
Yeah. So
So it's alpha squared plus z1 squared is z1 squared.
right.
Which means you're taking square root of that. Okay, now how would you plot that thing? Because this is your omega, and here you need to plot that thing. How would you start to plot that kind of thing? How should it look like?
Like a 1 over x.
1 over x plot looks
I want to be sure that's
like that. This is 1 over x, right? So this does not look like 1 over x. First of all, it has to be positive all the time. Right, for positive omega and for negative omega, it's still positive. Because this is omega squared, and alpha is constant, and also positive constant, and it doesn't matter in that case. So how does this function will look like graphically? Any strategy for knowing how it looks like? I mean, I'm not asking you to plot point by point, right? I'm not asking you for precise plot, but what is the overall shape? How it should look like? How you think even? I'm giving you some function, and you need to know how it looks like. Like what is overall shape? Is it hyperbola, parabola, 1 over parabola, or maybe arctangent kind of shape like that, or what kind of shape? Gaussian shape, bell kind of curve, or what shape it has?
Bell shape,
Why bell shape?
because as omega gets bigger, the denominator gets bigger,
So this is how you think about that. First of all, let's start with one point which we actually can compute. Right? What is that point? 0. This is the easiest one. So what is the value of that point at 0? Yeah, it's 1 over alpha. So it starts from here. Will it be greater than that ever for any other omega? Or this is our maximum point? So this is maximum point y. Because this will become only larger if you add in here any number. Right? So since denominator getting higher and higher, when omega getting higher, or more negative or more positive, doesn't matter. It will be bigger and bigger number here. So 1 divided by bigger and bigger number will become smaller and smaller. So it has to go somehow down. Will it be ever 0? No, because this will be 1 over something positive, right? So it will never get to 0, so it has to approach 0 somehow, but it will never get there. Now, what should I draw from that side?
the same thing.
The same thing, it's complete symmetry here. Why is that? Because it doesn't matter if omega goes positive or negative, it's square. It will be exactly the same number. So it should have mirror symmetry here. Not that I know how to draw completely symmetrical things, but something of that kind. No, not exactly. But you got the picture. This is how it looks like. This is amplitude spectrum. Now, how about phase? So let's compute the phase. So what is angle of x? How do you know the angle of 1 over angle of 1 over hypoplagio? How do you know what is that angle? How can you compute that angle? We can use conjugate, yes. Conjugate. Good idea. You can multiply by conjugate here and there, and then you will convert it into regular rectangular coordinates. Easier than that, since this is 1 over something. So what is angle of 1 over something? Complex numbers. What is angle of 1 over some complex number? Short reminder. This is minus the angle of the denominator. And it's 1 over. Because it's angle of 0 minus angle of the bottom part. Right? It's like angle of A over B is angle of A minus angle of B. Like in polar coordinates, remember. Okay, so what is angle of that thing here? We are talking about that angle. So what is that? What is the angle of complex number? You use it all the time when you convert into polar coordinates, right? So what is the formula? It's just conversion of that alpha plus j omega into polar coordinates. You have triangle. 90 degrees here. This side is omega, this side is alpha, this is theta. So what is theta?
It's
You don't
inverse
understand.
tangent.
So tangent of theta is omega divided by alpha. So arc tangent of that thing is what you need, right? Also like that. This is your end. Okay, now I want to plot how it looks like. Again, how arc tangent looks like.
So as omega increases, it gets bigger. When it's 0, it's 0.
So pay attention that
Constant.
arc tangent looks like that. This is the overall shape of arc tangent. It looks like that. Between minus pi half to pi half. Right? Asymptotically it goes to those two. This is arc tangent. But we have minus arc tangent, so how it should look like? Flipped, upside down. It will look like that. Something like that. So this is our phase spectrum of that kind of signal, of theta. Can you interpret what this thing means? Like what it says about that signal? Bell-like shape. I'm not talking about specific formula, I'm talking about just overall shape, how it looks like. What we can say about frequency content of that signal.
Mostly low frequency content.
I'm sorry?
Mostly low frequency content.
Yes, so this signal is mostly low frequency content, and as it goes with higher and higher frequencies, you have smaller and smaller amplitudes of those components. Okay, getting smaller and smaller gets faster and faster frequency. Is it reasonable? Like, would you expect something like that to happen? Pay attention what that signal is. That signal looks like that. This is that signal. It will look like that. Starting at 0, and then starts with 1. This is our x of t. Right, something like that. It's exponentially going down. Starting at 0 time, and at 0 time it will be alpha times 0, step at 0, which is basically 1. Right? So what do you expect from that kind of signal, that kind of distribution? What? Is it reasonable? The answer is yes, but when you're talking about reasonable, you always need to say why reasonable. What is the reason then?
So this is
Keeps going, it decays, and then it's
So where do you see here high frequencies and where do you see low frequencies?
At the beginning.
So that part is a high frequency, low frequency. It's very low, and amplitude also low, right? It's amplitude 0. So it's not really affecting anything here. Now, how about far away here? Is it low frequency, high frequency? Also low frequency. So most of the time it's flat, right? Just constant. So it's 0 frequency. Now, what about the jump? It's very high frequency. It includes all of the high frequencies, and not only high frequencies. It includes almost all of the frequencies. Because you have strong change here, this is where strong high frequencies happen. And this is why you have all of the part here and part here in the change. Everything else, just low frequencies. It's slowly changing here, not changing it over here, so nothing interesting happens. But in the jump, you have a lot of content, and this is what happens there. Okay? All signals that are smooth and changing slowly have only low frequencies. All signals which have some abrupt changes, they have high component of the strong high frequencies. Okay? Any questions? Surprised?
So at the areas where there's a quick jump from, like, say, at the instant of 0, that's the high frequency, and then everywhere else the frequency pretty much is that.
Yeah, so even step function, if you even remove all of that exponent and leaving only step function, it will have something similar to that, okay? Because it has flat, but then you have big jump, and in that big jump, you need a lot of high frequency to model it, okay, in that really short interval of time. So you need very high frequency to show something like step function, or very close to it, right?
So that moment in time is representative as right there at the center of the amplitude.
So that moment is represented on the
How wide it is
tails.
on the tails.
Yes.
Why is the high frequency? Oh, because as
So this is
yeah,
high,
as the,
this
yeah,
is frequency.
right. So as it
So
gets
high frequency higher goes that way. 0 frequency, which is DC, is here, like it's constant. Constant is here, high frequency is there. In spectrum. Question?
So, but like thinking of like an audio signal, like a high pitched noise. I mean that, and it's just constant. It's like a high sine tone at like 15,000 hertz.
It will give you some energy here on high frequencies.
Right, but it's you were saying how when the signal changes or there's jumps, that's a lot of high frequency content. But that's
So jumps are including all of the frequencies. It's not exactly true. Not all of the frequencies, but many of the frequencies. Generally, it gets like every second frequency, which is jumps of pi 2, counting pi 2. Like oscillation, then twice that oscillation, then 4 times oscillation, and so on. So you get all of the, like with Fourier series, you get all of the odd frequencies.
Sure.
Right? The same thing happens here, because this is coming from.
But even with
same
like
source.
a pure sine tone at like 15,000 hertz, it would, if you did the Fourier transform, you only have a peak at that frequency.
Okay, so you're talking that you can get high frequency without having actual step. True, yes.
Right. So it's just like a different case. That's
This is different case,
okay.
yes.
So
You still can have some amplitude here,
right.
okay, without having step function. So step function is giving you more Z kind of slopes, okay, which are including multiple different frequencies, which are not really visible in Z1, right? When you're talking about harmonic functions, which are including some of sine waves of some kind, it's a little bit different because you will not have continuous function here. You will have just deltas.
I mean, if
Okay,
you're
specific
playing
frequencies.
guitar, there's
Yes, so you will have just sparks.
right decreasing.
Yes,
yeah,
decreasing
from the
sparks.
fundamental.
Yes.
Yeah.
This is exactly what you will see. Any other questions? Okay. So now let's see a few tricks. Another example. Find Fourier transform of the following signal. The signal looks like that. It's x of t. And the signal looks like that. Like m letter. It starts with 0, ends with 0. Between -1 and 1, it gets that way, and then gets that way. Maybe we can use color here to emphasize the actual function. Okay, that one. How can you find Fourier transform of that kind of function? So there is trick involved. Clearly you can do that technically by just putting that function here. So you put in that as piecewise function. You already learned how to write that as long expression with u, with step functions, right? So you can say that this function is minus t, this function is t, right? So in the interval between -infinity to -1 it's just 0. Then between -1 and 0 it's minus t, and then between 0 and 1 it's just t. And then you're integrating on those multiple intervals, multiplying the t by exponent and finding what is integral of minus t times exponent. Then second one is plus t times exponent, adding them together, getting whatever you need to get. Okay? Possible. Is there any other way without computing the integrals? Solving it graphically and using table?
I mean, you still split it up piecewise, but then
You don't need to split it at all.
don't you need a different table entries?
There is just a cool trick here. You want to write that as sum or difference of something that you have in the table. And in the table you have triangles and you have rectangular pulses, right? You have rectangle between 2 points and you have triangle between 2 points. The triangle looks like that. And you have transform for that thing. It's called also TRI, triangle. Okay, so you have transform, which will be like that. The Fourier transform of triangle is sim function squared. This is a transform. And also you have something like that, which is called rectangle. Now, this rectangle is not between -1 and 1, but in the table is given minus 0.5 and 0.5. This is what you'll get in the table. Fourier transform of that thing is just simple thing.
Oh, it's just the difference between the rectangle and the triangle.
No, not exactly. Why? Because it starts at minus 0.5 to 0.5.
Yeah.
Right? So you have to make it, you have to stretch it to -1, 1. And then you can do this one, which is between -1 and 1, minus this one. And that's exactly what it is. Right?
Mm-hmm.
So what you want to do is to find transform of that thing. So what is that thing? So if this one is rectangle of t, so this will be what?
Yeah.
Stretched one, right, twice. 0.5t.
I can answer correctly.
Yes, that's all correct. Now, how we do from this one to this one? What we need to use? scaling property, right? Fourier transform scaling property. So let's use it. Okay, so this thing will have Fourier transform. And this is, just to remind you, what is scaling property. That x of at is transformed to 1 over absolute value of a, x of omega divided by a. This is scaling property. You cut it in the tables. So all we need to do is basically to divide by absolute value of the scale, right? And omega also divided by the same value. So what is a in that case?
1/2.
Yeah. This is what we have. So let's transform it. It will be twice. So we multiply by 2. It's 1 over 1/2, which is 2. Sync. And now, instead of omega divided by 2 pi, what we will have?
Omega over pi.
Omega over pi. You basically multiplying by 2. It's like dividing by 1/2. Any questions so far? So this is Fourier transform of that thing. Now, what we need to do? Now we have Fourier transform of that thing and Fourier transform of that thing. What is the answer for that thing then? Basically, x of t equals that rectangle of t over 2 minus triangle of t. Right? This is what it is. From linearity property, now we can just subtract the transforms. And that's it. So you get this one, which is here. And minus that one. Basically, that's it. Any questions? Okay, let's try to blend both physical description and trees. Yes.
Are the drawings of those in this? Or is it just these?
So you have that at the beginning, on the first page, formula pages, you have description of what triangle is and what rectangle is. That's this one and this one. You can draw it if you want. But this is how it looks like.
Okay.
Like, look, rectangle is defined between 0.5 and minus 0.5, right? So its absolute value of t should be between plus minus 0.5. In triangle, it's between plus minus 1. The value of the t is between plus minus 1 and amplitude is 1. Because when t equals to 0, this one will be 1. Rectangle is also amplitude 1. So it's like difference of step functions. Any other questions? Okay, now try again to make a drawing. Does it look like round?
That's what I see.
Looks beautiful around the house.
First powerful.
What is that?
Walls?
No,
Poles?
that's really poles.
I would get. I don't have a poles.
See, I'm getting better. Drawing. It's power poles.
Not clothing
With
line?
some wires in between.
Not clothing line?
Maybe. Depends. It doesn't matter those questions. Now, so you have some wires between the poles, and because of the winds, disturbances, and so on, they are oscillating, vibrating. Okay? And the middle point here is going up and down with some given frequency because of the wind, for example. Do you want to model the oscillation? Okay. And the signal will be like that. So this is what we will be saying. So with disturbing those power cables, you have oscillation compared to the rest position. Okay, so those wires obviously have some rest position, which is just flowing somewhere in between, and then wind is doing something like that around the resting point. We are modeling that movement as oscillation as a 8 cosine, something periodic, 2 pi ft, which is basically omega t, plus pi over 5. This is some phase, and this will be in centimeters. We want to find spectrum of the displacement signal. So first of all, 3 times per second, what is f? 3 here, 3 hertz. Let's take it, for easier computation, let's take it 5 hertz, 5 times per second. It'll be easier to compute. Okay, how do you start to solve the problem?
Look at tables.
Yeah.
Tables of what?
Transform. Can we go ahead and replace 2 pi f with omega? Or do you want to ask that?
So first of all, you want to put f inside of that thing and to make it a little bit simpler, maybe.
So 10 pi.
So you'll have x of t equals 8 cosine 2 pi 5, so it's 10 pi t plus pi over 5. Basically, it's the same thing as saying 8 cosine omega 0 t plus some phase, right? In that case, this will be omega 0. Now what? So you have multiple things in the table which fit exactly that. So first, it's just using table for 8 cosine whatever. You will not have 8, of course, but you'll have just cosine of omega 0 t plus theta, something like that, right? And then you just apply it to that signal. Let's see what we get. So in the table, you will have those things. You will have cosine omega 0 t plus theta goes to pi e minus g theta delta omega plus omega 0 plus e g theta delta omega minus omega 0, and that's it. This is what you have as a table. You can use it as this, just applying omega 0 here is 10 pi, and that is pi over 5. And then you multiply both sides by 8, right? So from the table, you just multiply this one by 8, and then this should be multiplied by 8 because of linearity property, right? So if you multiply that one by gain, here you need to multiply by the same gain.
You just multiply by the whole equation.
Yeah, so 8 cosine 10 pi plus pi over 5 will be transformed into 8 pi exponent minus j, and now that is pi over 5 delta omega plus omega 0, which is 10 pi here, plus exponent j pi over 5 delta omega minus 10 pi. Okay, so this is fairly easy. But what if I'm asking you not to use that formula and to use anything else you want? Can we prove that kind of formula? Because this formula could be developed from other formulas in the same table.
You use a split.
No, not really.
Okay.
Actually, I don't know, so I never tried. Maybe you can get out of that somehow with earlier equations. You can try. So let's say the only thing you can use for that is that thing. So another thing that you have in the table is that cosine is transformed to pi delta omega plus omega 0 plus delta omega minus omega 0. How we can get to that formula?
Time shift.
Yes and no.
Safety.
So this is definitely time shift, but time shift of what? What you need to do, you have cosine 10 pi t plus pi over 5. What you need to do is that formula 8 times. What you need to do is that formula to get to that format is time shift. Because time shift will look like that, right? Cosine of omega 0 t minus t0. Something like that. This is time shift. How can you bring it to that kind of shape?
You know,
You want to bring it to that form, something like 8 multiplied by something like that. How do you do it?
add to it. You add to it.
What do you add to? So this is still 8 cosine 10 pi is your omega multiplied by t minus or plus what? Something. So this is what you want, right? You want it to be t minus something plus something. This is time shift. So what should be here?
I don't know.
Or no, 1 over 20.
20.
Sorry. No, 1 over.
This is algebra. That's exactly what it is.
Whatever 50.
Yeah, that's better.
Because 10 pi divided by 50 will be 1 over 5. will be 5 pi over 5. Okay, if you multiply 10 pi, 10 pi divided by 50, 10 cancels with 50, you get pi over 5.
But don't we want to
And
add,
it gives you 10.
don't we want to add?
So this one times t, which is here, and this one times that one is that one. You're just making common multiplier.
Should we be adding 1 over 50?
Adding, sorry?
Would it be added? 1 over 50? Not,
It will be added,
so you just.
plus 1 over 50. Okay. Now we can use timesheet. Right? What's that say? Now, what do you know on timesheet property? It just multiplies by exponent j omega tau, or t0, whatever. Okay, let's see what we get from that. So 8 cosine 10 pi t plus 150 is translated into 8 pi, and then delta omega plus 10 pi plus delta omega minus 10 pi. This is still the same thing. And then time shift. Time shift will be exponent j omega 1 over 50. Does it look the same thing like that? No, not really. So there we have one with negative j omega something, one is positive j. You know, kind of different, right? Sounds misleading. Is it the same thing? What do you think? Is that the same thing? So this thing and this thing, this should be the same or not?
Should.
Do you believe that this is the same thing? Like you have here j pi over 5 and minus j pi over 5. This part is similar, this part is similar, this part is the same. This one is completely different, and this one is completely different. Is that the same thing?
Yes.
Really?
Yeah.
Who thinks it's not?
When you shift it in times, you change it later.
Okay, who thinks it is the same thing?
So there's a third option.
Okay, who is not saying? You need to believe to math more, right? This is exactly the same thing. Let's see why is it the same thing. So we have 8 pi exponent j omega 1 over 50 times delta omega plus 10 pi plus 8 pi delta omega minus 10 pi e to the j omega 1. Now, where this thing is not zero, what is the point? This is the only actual point where that entire thing is not zero. So what is delta times that thing? Let's take on the top part. So where delta, you know what delta is, right? It's like single point up to infinity, everything else is just zero. So if you multiply zero by whatever, by exponents, by constants, who cares?
So
It still will be zero, right? So it will be not zero only at one point. So what is that point?
Infinity?
No. So delta of t equals 0 at t equals 0 and infinity otherwise.
Oh, minus 10 pi.
You'll get minus 10 pi. When omega equals minus 10 pi, this thing will be infinity. Other than that, it will be 0 everywhere. Now, this means that you multiply only one point by that exponent. when omega equals to minus 10 pi.
Oh,
Right? This will be the only point where this thing is not 0. So you'll have 8 pi, so the same thing like 8 pi, exponent j omega minus 10 pi divided by 50 times again the delta. And the same thing here. Where this exponent will be not 0, but this one will not be 0, only at omega equals 10 pi, right? Positive 10 pi. The same thing here. So it will be exponent j 10 pi divided by 50
Is it,
delta omega minus 10 pi.
is the delta not supposed to be, the delta t, isn't it supposed to be infinity at 0 and then 0
Yes.
else?
Not at 0,
No, I mean,
at
like,
whatever
not the
is side
equation,
equals to
not the
0.
equation, the definition.
yeah, your
Is this one?
definition, your
Right.
infinity
Isn't it
backwards.
infinity at 0?
Yes.
Yeah. Okay.
Sure. I'm wrong. You're right.
Okay. It's the little wins that keep me in. It's the little wins.
Good job. That's correct.
Gotta keep it going.
Yeah. You have to be around.
Good to see you today.
Just check.
Okay. Where's my bonus points?
You missed one.
You didn't give me a chance.
Yeah, I ain't got to that point yet.
Yeah, as I'm going through it, I notice when I'm writing it down, and I have to look up and then I
Okay, so now 10 divided by 50 is definitely 1 over 5 by, so this should be hopefully the same thing like we had there. Good. Right?
Yeah.
Any questions so far?
So everywhere there's a delta, you have to consider the definition of delta just for that argument, right? So if it's
Yes.
a summation of them,
So
or-
delta will stay delta,
Right.
okay? You will not change it. But the coefficient you multiply by that, or function you multiply by that, essentially will become a number.
okay.
So no matter what kind of function, it's like that. So let's say you have some, those are your x's, and then you have delta here. You multiply it by function, whatever. That thing is exactly the same thing, like taking that point, multiplying by delta. And this is exactly the same function here, so it's delta times that number at that point. Right, you're just taking value of that function, you're just passing through the delta, and multiply that as constant, because everything else will be multiplied by 0, so you can remove that point and make it 0 here, right? Except that one point, which is multiplied by delta.
So you won't ever have like simultaneous deltas multiplied together, or
You might have multiple deltas. Let's say you have 2 deltas, okay?
Right.
Like that. So you're taking that point and that point. Everything else between will be 0.
Okay. And that
Right?
could
So
be-
this delta will be multiplied by that value, and this delta will be multiplied by that value. Whatever the value is. That's exactly what we did previously. So we had 2 deltas.
so is that kind of like how that is set up right there, where you have
That's
the
exactly how it's
delta added with this delta? They're never really going to be
Yes.
multiplied together.
They never interact, right? So they are different
That's
places.
what I'm saying. It's an illogical argument to have 2 different deltas multiplied against each other. Like if that was somehow.
Multiplication of 2 deltas which are not exactly the same place
Right.
is just 0.
Correct.
So it
Okay.
no sense to multiply
That's-
deltas at different
that's-
places with 0.
That's where I'm trying to get to.
Yes. Okay. Now let's try to plot spectrums.
This one. Very good.
That's one part.
Okay, so we want amplitude spectrum of that thing, phase spectrum of that thing. How it will look like? What do you think? So this is a little bit tricky question, actually. So this is your axometer. This is your complex spectrum. Now you want amplitude spectrum, which is absolute value of that sum. What is absolute value of that sum?
absolute value of their coefficients added together?
Absolute value of the coefficients, yes. And what is the absolute value of the coefficients?
It's e to the pi I.
So what is absolute value of that thing? 8 pi. Absolute value is 8 pi. What is absolute value of that thing? No matter what you have inside. It's e to the j whatever. J delta. What is absolute value of that thing? And what is that thing? This is complex numbers. For any delta. Is it different for any delta? So what is the value?
E to the
Absolute value of e to the j delta.
One.
E to
Yeah.
Unit circle.
It's a unit circle.
Unit circle. Radius of unit circle is
Big guys
1.
go crazy.
Okay.
It's 4.
Unit circle radius 1 for any angle, no matter where you go to which angle. And you can prove it easily. This is cosine squared plus sine squared and square root of z from earlier theorem. So what is that thing? Cosine theta plus j sine theta. Again, Pythagoras theorem of cosine and sine will give you cosine squared plus sine squared, which is trigonometric identity is 1. Okay. Now what? So this is 8 pi times 1 times what?
Say again? What was that?
So let's take only the first part, okay? You want absolute value of the first part. It's 8 pi times 1 times something else. You need to put that thing.
1.
1. Absolute value of delta is 1.
Or 0.
0. We have multiple options: infinity, 0, 1, 2, 5, and many other numbers.
The EJ to the infinity of 14. I lost it.
E to the j, whatever it's 1. Okay?
Okay.
We know that from complex numbers. But how about delta? Absolute value of delta. What is absolute value of that function?
The same thing.
First of all, it's a real function. It's not even complex. So is it always non-negative?
Yes.
Yes. So the absolute value of non-negative function is itself. Right. So this is what you get. You get 8 pi times delta plus 10 pi and then plus delta minus 10 pi. Same thing. So this is what we need to plot. Now, how we plot delta?
Straight up.
Some arrow which is going up, right? Good. This is omega.
Just be spikes.
This is x omega. So one point will be here, one point will be here. What are those points? So this should be symmetrical.
Plus or minus 2 pi.
So this is 10 pi, this is minus 10 pi, and you'll have two deltas here. One goes up, second one, hopefully the same height. Okay? The height that you are drawing is coefficient of delta and not real value of the delta, because real value is infinity. This is just going to infinity. But it's 8 pi times going to infinity. Okay? So this is your amplitude spectrum. How about angle of that thing? This is even more interesting. There are multiple cases here. So what is angle for, let's say, omega equals 5? Yes. Hmm? How about number 5? Do you like number 5? You can pick more or less any other number if you don't like it. So how about angle of that thing at omega equals 5?
At what point?
Omega equals 5.
Okay.
5 radian per second. So what will be that thing for omega equals 5? So it's 8 pi e to the power of something delta 5 plus 10 pi. What is 5 plus 10 pi? Plus 10 pi plus 5. So delta is that number, what it will be?
0.
0. So 0 times whatever, plus 8 pi e whatever, delta of 5 minus 10 pi,
0.
still 0. So what is that entire thing?
4.
0. Good. It's easy to compute. It's 0. How about most of the other numbers? Except 10 pi and minus 10 pi. It's still 0. So what is angle of 0?
Angle of 0.
Yes, it's 0. The only difference is when omega equals 10 pi, omega equals minus 10 pi.
It would be like,
That's negative.
Right?
it would be like 90
It's also some points where you can't have some difference. Technically speaking.
Would you write those as like 90 degrees or something like that? Or would that be
90 degrees?
Make it vertical?
What do you mean?
Well, x of omega at the omegas when they're not 0 to infinity, or do we put an angle on?
This thing?
I don't know. Never mind.
So this thing will be at angle, 90 degrees, or minus 90 degrees, yes.
Yeah, those are the angles.
Those are giving you some angle, but those are real numbers which are 0 or infinity. Now when it's 0, it's 0. When it's infinity, it's something with some angle. Okay? Now, so what happens when this one equals 10 pi?
It's 0.
0, so this part is there. How about this one?
8, 5.
So this one now is something positive, right? Positive infinity. And this one is also some constant number, real number. This one is complex number. So what does that say? J pi over 5. So this thing will be pi over 5. Angle, right? How about minus 10 pi? So this thing will be 0, obviously. And this will be
Infinity.
infinity, positive infinity, times that thing, times that thing. So this thing is not changing the angle, right?
Yeah.
This thing is changing. So it will be minus j pi over 5.
Minus
Minus pi over 5.
L 0.
Else 0. Okay. So now we just need to plot it. It will look like that. You have 10 pi minus 10 pi. At 10 pi it will go up. Minus 10 pi it will go down. Pay attention, it's not delta anymore. So it will be pi over 5, minus pi over 5, and 0 otherwise. And this is n of x omega. Okay? Pay attention that this is not delta, this is number plus minus pi over 5. Now, the trickiest question here, is that thing discrete or not?
No,
Why not?
it's continuous because it has a case for the entire spectrum of line.
That's correct. This is not discrete case. So we see only kind of 2 deltas here and just 2 points here sticking out. We have value for each other value, which is here. So it's actually 0, 0, 0, 0 until it jumps here. And then again 0, 0, 0, 0. It's completely continuous. Question? Okay, thank you.